Hello, my name is Brian Hill, and I'm a developer on DoIT's Enterprise Integrations team in Application Infrastructure Services. Today I'm going to describe how I'm trying to apply software engineering principles and practices to our use of the Terraform tool. Terraform is a free open source tool that wraps the vendor APIs of many cloud and software services with a common syntax, HashiCorp configuration language. It allows you to specify the cloud and software components you want to deploy, such as virtual machines, load balancers, and Lambda functions. The command line tool will look at your current configuration, compare it to the one described in the Terraform plan, and modify the infrastructure to match the plan. There are plugins called providers for many cloud and enterprise scale services, such as AWS, Azure, Google Cloud, and vSphere, which means that a single group of Terraform files can manage infrastructure across multiple clouds and platforms. A Terraform plan is a directory of Terraform source code files that contain descriptions of cloud components that you want to create and manage. These descriptions can include references to things that weren't created by the plan and already exist, and you can also import references to existing infrastructure to start managing it with Terraform. Terraform does not scan your cloud accounts and take everything over. It only affects components that are managed by the plan being applied. In order to keep track of which components it manages in their current configuration state, it stores the current state of the things managed by the plan in a state file. A Terraform State file is a JSON format file created and updated by the Terraform tool and should not be edited directly. It can be local on disk or remote in the cloud over various protocols. In our examples, we're going to store it in S3 in a private bucket. It reflects the current state of the infrastructure described by the plan and should be kept in private and not in Git, since it may contain credentials or other sensitive information, depending on what you're managing. One of the ways that Terraform differs from other ops tools like Puppet or Ansible is that Terraform allows you to describe what you want as an end state, and it will figure out what to do in order to create that, as opposed to having to know all the low-level commands to do the same thing. The provider plugins that wrap each cloud services APIs, such as AWS, are currently developed by the vendors themselves. AWS develops the AWS provider for Terraform, so it stays up to date with changes and new features in the AWS API space. I don't want to get too deep into HCL syntax in this talk, but a brief primer seems in order. Cloud components are represented by blocks, which start with a block type, in this case resource, then a label indicating what type of cloud component it is. In this case, it's an S3 bucket on AWS. Finally, there's a label that acts like a local reference to that component. Here, that's website origin. The rest of the arguments inside the block match the settings you'd see if you created an S3 bucket manually in the AWS console. You can see near the bottom that arguments can be more than strings and can be objects with their own attributes, such as the website section has for index documents. I'm going to refer to 6 types of Terraform blocks in this presentation. Provider blocks configure the account associated with the service. For this one, we are configuring our AWS account and the region that we want to use by default. This block also has a list of allowed account IDs that this plan can be applied to, which provides a safety measure if you're working with more than one AWS account. We looked at this type of block a moment ago. Resource blocks create and manage components, this one being an S3 bucket named origin.my.presentation.demo, and referred to as my bucket. If you need to refer to this bucket in another part of the plan to connect it to something else to it, you'd use the notation of AWS S3 bucket.mybucket. Here's a data block that queries AWS for a pre-existing VPC named test tier and has a tag named tier with a value of test. Data query references are read-only, so nothing in this plan will modify or delete the AWS VPC referred to here. This is one of the ways that you can loosely couple different plans, as I'll cover later. To refer to this data block and the VPC it represents, you'd use data AWS VPC.test. Since it starts with the data keyword, Terraform knows it's a read-only reference, among other things. Data blocks are used also to generate JSON data for AWS IAM access policies. I find this syntax slightly more readable than the JSON version, but either can be used in Terraform for IAM policies. Variable blocks are values that are collected at runtime when you preview or apply the plan. They allow you to write your plans in such a way that all of the commonly changed values can be set when you run the plan, such as specific application versions or scaling configurations. To refer to a variable elsewhere in a Terraform plan, you can prefix the variable name with var, such as var.app version. Output blocks allow you to print a value that's calculated at runtime on the screen and also to provide for export to another plan, which I'll go on to later. Finally, module blocks represent calling another plan or a module. This is the main way that you can start to organize the Terraform code and reuse common or standard definitions. I'll cover modules later on as well. There's also some syntactic sugar available should you decide to use it, including string manipulation, some basic control structures, and built-in functions that calculate subnets and other relevant capabilities. For myself, I try not to do too much of this stuff since I think a simpler, flatter plan is easier for others to understand, but your mileage might vary. When you run Terraform on a plan, it compares each component described by the blocks in the plan to the state recorded in the state file. If the configuration differs from the plan, it will modify the configuration. If the component doesn't exist, it will create it. If a component is no longer in the plan but is referenced in the state file, it will delete or undeploy it from the cloud. It offers a detailed preview of what will happen when the plan is applied to infrastructure and requires you to confirm that the changes should be made. You can also save a diff of the changes that will be made to a file and examine it offline as part of a merge review. The typical workflow when using Terraform is to edit the plan, then run the Terraform Plan command to see if it looks like it will end up with what you want. If not, continue iterating between editing and running Terraform Plan. Finally, when it seems correct, run Terraform Apply to modify your infrastructure. Like most software, Terraform plans often start small and then grow larger. How can we organize the plans so that we don't box ourselves into a corner later or end up with a lot of friction as we use Terraform to maintain our cloud components? I'm going to borrow some terminology from a presentation by Nikki Watt from OpenCredo to describe various ways to organize Terraform plans, since it characterizes different stages of organization fairly well. The first type of plan organization is the first one people usually create, and that's the Terralith. Everything about the infrastructure is contained in one grand unified plan, including test, dev, prod, and everything else needed. I should mention that splitting the Terraform plan across more than one file is no problem and very helpful in keeping the code organized. The command line tool effectively concatenates everything together before it runs the code, and being a declarative syntax means that ordering doesn't matter. So you can organize the code for a plan however you wish. As long as the files are in the same directory, it's part of the same plan. This plan is just going to create a very simple website with two tiers, test and prod. We're going to serve the site from an S3 bucket, so there aren't many components to create. We split up the plan between a few files to organize the Terraform blocks into test and prod components, as well as a common iam.tf file that contains the definition of an S3 bucket policy. The main Terraform file contains just the provider configurations for AWS. This shows one way to set your AWS account credentials, and since they are set by variables, when you run this plan, Terraform will prompt you to enter these values. There are other ways to provide your AWS credentials to Terraform, including by setting environment variables. The provider block also specifies that the default AWS configuration will be US East 1 or North Virginia. That means that all components will be created within US East 1 unless otherwise specified. This is the access control policy that we will attach to each S3 bucket, which allows anyone to read the contents of the bucket since it's a website. This is the same information you'd need to set it in a JSON version, such as you generate in the AWS console. Again, I find the HCL notation to be slightly more idiomatic for Terraform. Either way, it ends up being converted to JSON and used the same way a native JSON version of the IAM policy would be used. Here we are describing the S3 bucket we want to use for the test tier website. You can see the reference to the IAM policy block we just looked at. Adding the JSON suffix tells Terraform to convert it to JSON data. Again, this is pretty much the same information you'd need to configure the same website S3 bucket manually in the AWS console. The output block at the bottom will cause Terraform to print out the website URL of the bucket when you apply the plan. Nearly every cloud component that Terraform can configure has a whole host of read-only attributes that are set after you apply the plan, based on the output it receives from the provider, which is AWS in this case. The Terraform provider documentation contains the complete specification of each attribute that can be set, and which read-only attributes can be queried or referred to. Finally, the same type of resource block will create the S3 bucket for production. Here we'll also print out the URL of the website bucket after the plan is applied. So this is kind of a terrible way to proceed for very long. All of our eggs are in one basket, so to speak. If we inadvertently change something and apply the plan without noticing it, it could potentially affect both test and production. By affect, I mean delete and or wipe out and recreate. It's hard to test changes this way since both test and production are in scope to be changed every time you apply it. Finally, it becomes harder to understand what's in the plan once it gets larger and more components are added, such as virtual machines or Lambda functions. A couple of basic safeguards are in order. Always preview the plan before you apply it. While you can use a local file for Terraform State, the file becomes a problem, since every developer that wants to run the plan needs access to the same file. It also might contain credentials, so storing it in Git is a bad idea. Finally, it's critical that all changes to the infrastructure that the plan manages are recorded in the state file. If two developers have it checked out and both run the plan, each might end up undoing the changes that the other one made. For this reason, it's recommended that you use a shared state file in cloud storage somewhere like S3. The S3 Terraform State code also provides a way to set up rudimentary state locking via DynamoDB to avoid having two developers apply changes at the same time. So now we're going to level up our use of Terraform and start using the Multi-Terralith plan. This simply means that we'll put the test tier plan in one folder and the prod plan in another one, so that when we are applying one of them only at one time. This way we can be sure that changes to test never affect production until we apply them to production. Here's the same code split into two different directories, and thus two different plans, one for test and one for production. We also added a block to store backend state in S3. Each plan should use a unique S3 key or file name so that you don't end up overwriting the state from a different plan. You can use the same S3 bucket to store state for any number of plans as long as each one uses a different S3 file name. The test bucket configuration is identical to the one we used in Terraservices. For the test bucket's IAM access policy, we are only specifying the test bucket that it applies to, as opposed to both test and prod in the Terralith example. The production plan is the same as the test plan, with changes to the state file name and the bucket name. We also set the region on the AWS provider to US East 2, so production will be in US East 2, while test is still in US East 1. As before, this is the same as the prod bucket in the first example. The access policy also affects just the production S3 bucket. This is safer than the single Terralith plan, since we are less likely to delete production inadvertently, which is definitely a good thing. However, now there is a lot of duplicated code between the two plans. Also, we will need to remember to manually copy any changes we make to the test configuration to production, which could lead to them drifting apart. The next stage in evolution of our plan is the Terramod, since we're going to introduce a Terraform module to reduce code duplication. A Terraform module is just a folder with a Terraform plan in it that is called by another plan. There's no special declaration you need to use in a folder of Terraform plans as a module. In other words, there's nowhere inside the module that states that it is a module, unless you have a README file in there. Here we've moved all the common code in the previous example into a shared website module. It's just another local folder at this point, but you can reference modules via HTTP, Git, and Terraform's own module repository protocol, among others. But it's easy to get started by creating a module locally and then deciding whether it's useful enough to share with other projects later. This has allowed us to shorten the tier-specific plans to a single file. Aside from the provider and backend state reference, the only thing we need in order to integrate the website modules to provide our tier-specific information to it. The module source points to the adjacent website folder, and we're giving it a value for the bucket name variable it requires. This is how you pass arguments to a module. Finally, we've defined an output block to grab the value of the website URL from the module itself and print it on the screen. The website module needs to have an output variable website URL itself defined in order for this to work, since we can only reference output block values in the top level plan. Prod is the same, with a couple of differences in the region, bucket name, and state file name. Now down in the website module, here's the variable definition for the bucket name variable we need to give it. It's idiomatic in Terraform modules to collect all the variables needed for the module in a file called variables.tf, and all the output blocks provided by the module in another file named output.tf. This allows other developers to quickly scan these two files and know what information is needed to incorporate it. Here is the IAM access policy and S3 bucket definition now in the website module. You can see the highlighted lines where the bucket name variable is used. Here's the output definition for website URL that we reference in the test and production plans. The provider declaration of the calling plan is inherited by the module by default, so you don't need to include account information in the module. Variables are the only way to pass values into a module, and output blocks the only way to get data back from it. Modules can be local or remote and can be nested. The components that the module creates and manages get saved in the calling plan state, so they shouldn't store their own. They generally shouldn't have their own provider block except in fairly rare circumstances such as cross-region or multi-cloud plans. Avoid having a module create too much, since it limits the ability to integrate with other modules. If your Lambda plan needs a VPC to run in, pass the VPC ID in via a variable instead of having it create the VPC itself. Also, the current idiom is to prefer a horizontal composition of modules rather than a deep tree of nested ones. The virtual machine plan should be next to the network plan, not inside of it or around it. Which brings us to the final stage of plan evolution, Terraservices. This strategy is meant to facilitate both multiple executable projects, such as microservices, or separate teams where each manages part of the infrastructure. It tends to be the most flexible as well. We're going to build on the previous examples of the static website and add a dynamic API handled by a Lambda function. In order to access what we need on AWS, we'll need to have it run in a VPC. So we'll need a network. There will be 3 Git repositories that all build required components. One for the website, another for the Lambda function, and a third repository that contains the Terraform plan to create the network components. The network plan is considerably longer than the ones we've looked at so far, so I'm not going to go over it line by line. It creates a VPC or private network space for the project and sets up the network gateways, subnets, routes, and other parts of the network. It's set up to require just 2 variables, the region we want it to be created in, and the logical tier name we want to use for it, such as dev, test, or prod. This designation is purely for our own purposes, but it also helps us find these components from the other plans. The tier-specific main files that we will use to create the test and prod networks are fairly short. The main purpose of them is to configure the provider and backend state storage, and then to call the shared network common module with the tier-specific values. Here's a peek inside one of the network plan files to show you how the tier value gets used. We're going to add 2 AWS tags to the VPC component that it will create. Tags are arbitrary key value pairs that you can set on many different AWS cloud components. These can be queried by Terraform, and they will help us connect the different components together. Here's the repository for the Lambda-based API that we'll add to the website. The Terraform plans included in a subfolder of the Lambda project create an API gateway and connect it to the Lambda for either test or production. In order to deploy the Lambda within a VPC, we need to be able to reference the VPC created in the network plan. We'll also need to reference a list of the VPC's subnets. While we could probably pass in the needed identifiers as variables, there would be a lot of them and would have to be kept up to date manually. Instead, we can use data block queries to look up the VPC in AWS based on the tags we set in the network plan. Here, for the test tier, we're looking for a VPC with a name of test tier and a tier tag of test. In the subsequent queries, we're using the ID value of the VPC we found in the first data block and then narrowing the search with the tags we set in the network plan. This creates a loose coupling between the network plan and the API plan that avoids the need to manually keep the values up to date. Here's the resource block that creates the Lambda function. We're using the values for subnet IDs and security group ID that we looked up with the data query blocks. This block also expects that the Lambda executable itself, for a node that's a zip file, is already in S3 waiting to be deployed. I'll describe how this fits into a deployment workflow shortly. Finally, the website project plan is identical to the original Multi-Terralith one. We'll access the API from within the website code, so we'll just need to upload new assets to the S3 bucket to get the web pages to fetch from the API. With each layer of the system in different repositories, it lends itself to different teams handling each with different rates of change. We'll rarely need to do anything with the network plan once we create the components, other than adding new things to it, while the API and website plans will probably change much more often. Each of these teams can work more or less independently of the other, and each can deploy their part of the project at any time. Getting to the actual software development workflow, now that we've organized the Terraform plans into project-specific separate plans, we can easily keep the Terraform plan for a project right with the project source code. You can use Terraform non-interactively by passing the variable values in as arguments on the command line and your AWS or other cloud credentials in environment variables. There's a lot of guidance that suggests that you should stage your executables outside of your Terraform plan and not mingle it in there. This means uploading something to S3, pushing a Docker image to ECR, or creating and uploading an Amazon machine image with Packer, and then have your Terraform plan deploy the executable from there. That's the strategy I'm going to describe. First, we're going to deploy the Lambda function using 3 steps in our workflow. We'll stage the Lambda zip file to S3 using the AWS command line tool. Then we will run Terraform Plan to preview the changes and save the output of the preview that describes the changes into a diff file specified by the out argument. If we're satisfied that the changes are what we want to have happen, we can feed the same stored plan diff file into Terraform Apply to guarantee that only those changes will be made. If something changes in the infrastructure in the meantime, like someone else also updates the plan or the infrastructure, Terraform will see that and stop the deployment to allow for more inspection before changing anything. Here's an abbreviated GitLab CI file that shows how each step in the deployment is defined. In the deploy test preview step, we'll first upload the zip file of Lambda code to S3, then we'll change to the included Terraform plan directory, call init, since we're starting with a clean checkout doing CI/CD, then run the plan step with the appropriate variables for app version and tier. We're going to store the diffa changes to be made in a file called test.tfplan and save that as a GitLab artifact. A developer can then download this file and see what Terraform is going to do. Finally, if we're happy with it, we can click the button for the manually triggered deploy test apply step and use the diff file to apply the changes and actually deploy the new Lambda software. Deploying to prod is very much the same, except instead of uploading a zip file from our CI/CD environment, we're going to copy the zip file we tested in test to the production S3 bucket and preview and deploy it from there. That way we can be sure we are using the exact same files that we tested in the test tier. In order to actually get from the first Terraform plan to the last one I described, without having to recreate all the cloud components in the process, you'd need to use some of the refactoring tools built into Terraform. The main ones are Terraform State, which allows you to modify the stored Terraform state directly, and Terraform Import, which enables a Terraform plan to take over a cloud component that it didn't originally create. This topic is complex enough that it needs a presentation of its own to cover, so I won't delve into it here. But if you find that you need to change a plan without modifying any of the actual deployed components, you should know that there are some tools available to do so. I'm hoping that this very brief description of how software engineering can be applied to infrastructure management was helpful. If you have any questions about this approach or Terraform in general, please feel free to ask me in the conference Slack channel or via email. Thank you.